Today's topic is carbocation rearrangements, and you may find these described as Wagner-Meerwein rearrangements, although the textbook that we use, Klein, doesn't refer to them as this. So carbocation rearrangements are where we have a carbocation that is not, well, all carbocations are not very stable, but it can rearrange to a new carbocation that's more stable. So I've got an example here of a primary carbocation. So remember, primary carbocations are where we have the carbon bearing the positive charge only has one alkyl group. So there's one alkyl group directly attached to that carbon. Because it's a carbocation, it must only have three substituents and an empty p orbital. And so the two remaining substituents are those hydrogen atoms that aren't drawn in. So this is an equivalent sign. This is drawing out that carbocation in a different way, showing the vacant p orbital and showing how we can stabilize that p orbital, that vacant p orbital, with overlap with the sigma orbital of this CH bond. So that sigma orbital, that CH bond, is helping to stabilize that carbocation, but it's still not very stable because it's primary. There's only one group here that's able to stabilize that carbocation. These protons, these hydrogens out here, are not able to stabilize through this hyperconjugation. And so if we think about this pair of electrons here, and I'll just draw them in, that bond there is signifying a pair of electrons in a sigma orbital. There's a sigma orbital, and there's that overlap that's stabilizing the empty p orbital. Now what about if that overlap became something a little bit more? What about if those electrons wanted to migrate with the nucleus they're attached to over towards this p orbital? What would happen then? Okay, so if we do that, I'll draw curly arrows from that bond or from that pair of electrons to that p orbital there. What we'll end up with is a new carbocation. So we'll have that carbon there. We'll still have the methyl group attached that's coming towards us, and we'll still have the methyl group that's going away from us, and there's going to be a empty p orbital left behind because that pair of electrons has migrated with the hydrogen to the atom next door. So now we've got, that's the hydrogen that migrated, and then we've got the two remaining hydrogens here. Okay, so now we've got a methyl group and a carbocation, but if we look at that carbocation, it now has three non-hydrogen substituents, and so therefore it's much more stable. It's a tertiary carbocation. Okay, so sometimes it's good to look at molecular models to see how these things work in 3D. So I've got a model of our starting material here. So what we've got, I'll try to align it the same as in the diagram. So here we've got the hydrogen-carbon sigma bond, and here we've got the vacant p orbital on that primary position, so the primary carbocation. And that CH sigma orbital is helping to stabilize that carbocation by overlap of that pair of electrons with that empty p orbital. Now what could happen is that hydrogen can actually, instead of just helping to stabilize through that sigma p overlap, it can migrate with its pair of electrons to form a new bond to that carbon there. This is going to get a bit messy with my model here, so I've got a new model to show you that. Okay, now we've got, see that green bond there? That's the new CH bond to that, what was the primary carbocation, and it's left behind an empty p orbital, and we now have a tertiary carbocation. So these two methyl groups here, I've not put the hydrogens on there just to make it a bit easier to see in the model, but each one of those is methyl groups, and this is a methyl group too. So now we have a tertiary carbocation, which is much more stable than the primary one that we started with. Now it's not just hydrogens that can migrate with their pair of electrons. And remember, if it's a hydrogen migrating, then it's hydride migration. It's hydrogen with its pair of electrons. But as I said, it's not just hydrogens that can migrate. We can also have alkyl groups migrate. So have a look at this carbocation here. This one is a secondary carbocation. So a little bit more stable than what we started with. In fact, primary carbocations are very difficult to form. But secondary carbocation, because we have two alkyl groups attached, so the third substituent must be a hydrogen. So we'll draw that out as we did before. We've got this carbon atom here has a methyl group, a second methyl group, and a third methyl group. And then we've got our carbocation with its empty p orbital. And now we've got one hydrogen substituent and one methyl substituent. And once again, we can, as well as just having overlap between this sigma orbital with its pair of electrons, helping to stabilize that carbocation through sigma to p orbital overlap, we can have that actually migrate across to that position, the methyl group moving with its pair of electrons to form a new carbocation. So there's our first methyl group going away from us. There's our second methyl group coming towards us. There's our empty p orbital. And now we've got this CH3 group that migrated across. And the two groups that are already there. Now if we have a look at this system now, that carbon atom, that is the carbocation center with its empty p orbital, has 1, 2, 3 alkyl substituents. So it must be tertiary, so we've become more stable once again. Okay, so carbocation rearrangements, we look for groups that can migrate, that leave behind a more stable carbocation. Okay, so good luck with these carbocation rearrangements, and may all your carbocations be stabilized.